Okay, hello everyone. I am Katherine Anarde and I'm a postdoc at the University of North Carolina at Chapel Hill. I'd like to acknowledge my co-authors, specifically Wei, Pat, and Feng Yang, who did all of the modeling work for me. So a quick outline for today's talk. I'm going to use field data to identify the important hydrodynamic processes during overwash. So namely how storm surge and wave setup can increase the mean water level and allow infragravity waves to propagate through a barrier island cut during overwash, as well as meteotsunami, or very low frequency oscillations, which we hypothesize are meteotsunami driven by tropical cyclone rain bands. I am then going to try to resolve these processes using several numerical models. This is my beautiful field site. It is an antecedent surge channel bisecting Matagorda Peninsula in Texas. So prior to Hurricane Harvey in 2017, I was able to deploy pressure transducers on either side of a barrier island, on either side of this barrier island cut within shallow groundwater monitoring wells. So some key findings from this hurricane. The morphological change was relatively small. So here I'm showing digital elevation maps 1 year before the storm and 1 week after the storm. One of the large changes was migration of the berm, or erosion of the berm landward by about 50 meters. Some of the sand which was deposited in the back shore. So this region right here, which is typically subaerial during quiescent conditions, and it buried our pressure transducer. So due to this burial, groundwater effects were important. Here I'm showing the groundwater effects were important for interpreting the pressure head. So here I'm showing pressure head in the back shore and in the back barrier for several hours during overwash. So here between -4 and -2 hours before landfall. So during this time, we found that the pressure head could be assumed hydrostatic with a fully coupled sand bed and water table. So here, each of these squiggles are infragravity waves. They were the dominant forcing during this time. And these infragravity waves were modulated by very low frequency oscillations, which are here shown in black. The largest infragravity waves were located on the crest of these very low frequency oscillations. And note that these infragravity waves are very small. The maximum peak to trough wave height was only 22 centimeters. So this is smaller than infragravity waves observed elsewhere in the world. And in the back barrier, the maximum wave height was 9 centimeters. So to model this, to model storm surge and wave transformation, we are going to use two phase resolving fully nonlinear Boussinesq wave models, namely cool wave and fun wave TBD. So these Boussinesq wave models are coupled with ADCIRC and ST wave to get at storm tides and offshore wave boundary conditions. So this project was initially for the Army Corps of Engineers to provide an intercomparison of different numerical solution schemes and dissipation parameters for these Boussinesq wave models. So here I'm showing the modeling domain. This is my barrier island cut, or my field site, it's not mine. And here I'm going to take a closer look at wave transformation during overwash. So on the top, we are plotting mean wave period, including infragravity waves and short waves, so over all frequencies. And on the bottom, significant wave height. The mean sea level is right here, and the channel throat right here. I've also denoted the frequency cutoff for the infragravity band. So both Boussinesq models are highly consistent in their predictions of nearshore wave conditions, but they start to diverge into the backshore and through the barrier island cut into the back barrier. So these model differences are probably attributed to differences in bottom friction and braking models. So cool wave uses an empirical braking eddy viscosity transport model, whereas fun wave uses no explicit breaking model. They also have differences in the wave maker, for example, frequency direction splitting and wave maker width. Okay, so comparing these model simulations to our observations of infragravity waves during overwash. So looking just at the mean wave period, here I've plotted our span of wave periods during overwash, which was between 86 and 120 seconds for the mean wave period in the backshore. And the mean wave period was slightly smaller than that in the back barrier. We can see that both fun wave and cool wave underpredict the mean period, even though the dominant period for much of the backshore and in fun wave is in the infragravity frequency band. Taking a closer look at the significant wave height. So here we're showing significant wave height for all frequencies. So I want to take a closer look at just fun wave. Here I've broken down the significant wave height into infragravity components. So I integrated over the infragravity bands, specifically for the lowest frequency infragravity waves, around 100 seconds, which is the mean period in the backshore. And we can see that the simulated infragravity wave heights are about 0.5 meter. And this is much larger than our observations of about 20 centimeters. But we do see a decrease in wave height into the back barrier in this model simulation. So to summarize, the Boussinesq wave models are under-predicting mean period and over-predicting infragravity wave heights, but generally doing a good job in the near shore. So future work, I need to work on modeling and improve the data model mismatch. So I didn't mention this, but we use pre-storm bathymetry. So I described the post-storm change or the changes to the morphology of the berm during the storm. So I'd like to try to incorporate post-storm bathymetry as well as different offshore conditions. And once I do that, I want to test a hypothesis that energy transfers are important to wave transformation across the downward sloping barrier island cut into a back bay with elevated water levels. So this is one of my interpretations from the field data that I couldn't discuss today, but I think it's important and I'd like to model it. I also hypothesized that these very low frequency oscillations are meteotsunami driven by tropical cyclone rain bands. And to look at that hypothesis, well, first, we know that meteotsunami can be triggered by tropical cyclone rain bands. I encourage you guys to read this paper by Lumin Shin and Maitane Olavarrieta. So here I'm showing the radar offshore the Matagorda Peninsula field site, both early in the storm, so at the beginning of the time period when we start to see wave flooding at Matagorda Peninsula, and we saw a large increase in bed elevation, and also during overwash. So here are the rain bands. So I also had a field site farther up the coast at Follett's Island, and at this field site, I had co-located pressure transducers to measure atmospheric pressure anomalies, as well as a pressure transducer in the surf zone. So here I'm showing these pressure anomalies, and the corresponding, or they correspond to very low frequency oscillations in the surf zone. So to test whether or not these air pressure anomalies could generate meteotsunami, I worked with Wei and Wan at Texas A&M to test their shallow water model with an added air pressure term that can simulate Prudman resonance. So very quickly, Prudman resonance occurs when an air pressure disturbance produces a small water surface perturbation in deep water due to the inverse barometer effect. This perturbation can grow in height as it travels across the shelf due to external resonance processes, specifically when the shallow water wave speed matches the speed of the disturbance. So this video is really quick. I apologize, but it shows how our measured atmospheric pressure disturbance propagating across the shelf towards our field site. So here it's just propagating across or along a straight trajectory, and it produces a wave on the order of 30 centimeters in amplitude. But there are many uncertainties in modeling these atmospheric disturbances, including the geometry of the atmospheric disturbance. We just allow the pressure to decay exponentially in the alongshore. We also found from radar that the forward speed of these tropical cyclone rain bands are highly variable, which is hard to model. And we are uncertain about their track, as well as the effects of rotation from the radar. So here I'm going to show another simulation where we try to rotate this air pressure disturbance. And on the right, I'm showing the output. So in black is the observed pressure, in red, the simulated pressure, and this was actually our largest pressure crest anomaly. And here's the water surface response. Blue is observed, red is simulated for a 20 meter per second forward speed along the straight trajectory, and the light red is along a rotational trajectory. So we match, or we can produce water level or water surface anomalies of similar height, but they don't necessarily match the period. So in the future, we want to try to incorporate contributions of wind into the initiation and growth of meteotsunami. So this was an important, Luminci and Maitani Olibalriatiev found that wind was important within their idealized modeling. We also need more field measurements, so better resolution of pressure and wind disturbances. And with that, I'll take any questions. Oh no, how do I stop?